Hello, everyone, and welcome to our presentation. My name is Janine Donnelly. I am the Manager of Webinars for IBM Systems Magazine, and I will be the moderator for today's event. Today's webinar, Beyond Capping, Significantly Reduce Z13 MLC with Processor Cache Optimization, is sponsored by IntelliMagic. Our featured speakers today are Brent Phillips and Todd Havicost. Brent has been working with IBM mainframes for over 30 years, starting in operations while in university and later as a system programmer. He's been working for IntelliMagic for over 11 years and is now responsible for the IntelliMagic business in the Americas. Todd is a senior ZOS performance and availability consultant at IntelliMagic. Todd's passion and primary area of interest over the course of his 38-year IT career has been ZOS systems performance. Prior to joining IntelliMagic, Todd spent 26 years at USAA in a variety of technical and management roles. Having been impressed with IntelliMagic solutions as a customer, he now leads IntelliMagic's efforts to reduce MLC software costs for customers. With our introduction complete, Brent, I'll turn the presentation over to you.
Great. Thank you very much, Janine. Thank you, everybody, for joining us today. We appreciate and respect your time, spending some time with us. We hope it'll be of value to you. The title here is talking about Beyond Capping because we know that for quite a few years now already, many sites have been looking at capping and implementing capping to various degrees in order to reduce the MLC cost. We also know that an alternative title would be prior to capping if there are some ways to reduce costs through capping through manual ways. There's also some products out there for automating capping. And one piece of advice right from the outset on the title slide might be to, our suggestion would be to actually look at some of the areas that we're talking about in this deck prior to executing an agreement for capping software. So if you're at that stage in your environment, a lot of those products may charge you based on the baseline and the savings they can incur. So our recommendation is to actually reduce your baseline prior to signing that agreement and establishing the baseline there just to keep the capping in line in an automated fashion, but your license charges will decrease. And really the same kind of comment applies if you're looking towards a CMP kind of agreement with IBM. I mean, they establish a baseline. So using some of the things that we're talking about here today to reduce your peak MSU usage prior to the establishment of that baseline can save you some significant money down the road. So a little bit of advice right at the outset. Today I'm going to talk a little bit about this idea of modernizing how we process and understand what's in the RMF and SMF data and what does that mean for both the performance and efficiency side of things. So introduce some of the concepts of what we're doing and specifically why we're doing it. And then Todd will take over and go through some slides on some of the concepts for processor cache efficiency in particular, as that's a newer area for most sites. And then he'll switch over after the concepts to an actual demo of our particular implementation with our product, which is called IntelliMagic Vision. So you can kind of see what he's talking about and how he got to some of the charts that he used. And then we'll wrap up at the end by talking about how you can see the same thing with your data. It's quite easy to send your data to us, and we'll spend some services hours helping you identify out of the data what we believe are yet unrealized opportunities for MLC reduction that the additional visibility we provide will enable. So we like to start out by talking about a couple of assumptions that we've had in the industry for many years. We know that the RMF and SMF data reporting processes have been around a long, long time, and there can be a tendency to think that it's about as good as it gets because we spent so much time customizing these reports, building the PDB, so on and so forth. But from our perspective and what we're doing, we really believe the greatest value in that data is still unrealized or unutilized because of the processes that we're using to understand what the data means. So hopefully that will become clear as we kind of proceed through the slide deck and the presentation. One example of that is it's commonly thought of by performance professionals that SMF is for forensics and trending, but doesn't really have value for real time because it's post-processing data. With our approach and what we're talking about and how you modernize, how you process and understand what the data means, the reality that we can actually prove through your historical data and showing you, what it would be predicting is that it can be sooner than real time is one way to say it, or actually avoiding a situation getting into a real-time status. So you can see problems prior to real-time monitors that are triggered more on symptoms of problems ever being triggered. That's kind of the objective of it. So that's actually a very significant benefit from a performance management standpoint that sites do not realize today. Most problems are still discovered only after they impact the production environment. One final assumption here that we like to challenge is about the CPUs. I mean, we've been trained for many years that the cost associated with the CPUs is just so significant. You want to run those things as close to 100% as you can in order to maximize cost efficiency. And that is no longer true as well. In fact, if you're doing that at your shop, you're probably paying more in net cost than you need to in a significant fashion, because the reality is with today's architectures, processor cache efficiency, one of the main messages out of this presentation, is going to be less efficient, and it's going to drive up your peak MSUs on your rolling 4-hour average. So hopefully that will become clear in the technical presentation that Todd does on why that's the case. So Todd and I are both part of a team of 70 people now at IntelliMagic, and this has been our focus in the 11 years I've been here, and even prior to that as well, is to take the performance and configuration data and really transform it not just into reports or information, but into real intelligence about where the risks are, where the opportunities are. So serving as a beacon with detailed knowledge about the risks that may be hiding under the surface. So that's really what drives us. That's our goal. And what it looks like from our perspective is this idea of modernizing how we process and interpret the RMF and SMF data. And essentially the key to creating this magic and this intelligence out of the data is by using embedded expert knowledge that's specific to ZOS best practices, to the ZOS specific infrastructure that's running your workloads, and automatically applying that to be able to interpret it and surface what it means, what's in the data, what does it mean for your workloads, not just what the metric is, but is it good or is it bad from a performance standpoint, from an efficiency standpoint. So using this expert knowledge, we can derive new metrics out of the data. We'll do some calculations to show additional things that are not available in the raw data. For example, we can show the throughput going through certain components, and with the knowledge about what those components are capable of handling in terms of throughput limits. That's a great example of how we can show this early warning to avoid a real-time issue by tracking every day how close to the limits of those components your throughput levels are. Applying best practices, as I mentioned, for configuration and performance management, and continuously checking that your configuration is adhering to those best practices to avoid issues surprising you. Balance and redundancy identification is also key, and it can be extremely time-consuming to get those kind of views in a manual fashion. So that's another great example of the benefits of applying this expert knowledge to the data and surfacing the results in the form of intelligence. And finally, on this chart, the last example of what you can get out of this is by correlating the knowledge of the physical resources and what they're capable of with the knowledge about the logical workloads and the logical configuration and systems. Correlating those two together is really the only way to get this good understanding of what is the risk in your infrastructure to handle the workloads that you're asking it to run, and where will that risk manifest first. So, or if if it's a problem that can't really be predicted, to be able to understand what are the resources involved and what are the root causes of this problem. So what's the difference? This can be actually applied in two different ways. What's the difference with what you're running today as a status quo with your reports and your PDB? And yes, there's some significant differences, and we've had customers that have actually walked away after decades of investing in that infrastructure just because of what the difference is. But primarily this focus is on some new approaches to understanding the data, which tend to rely on statistical analysis. So you can recognize anomalies in data patterns, but what we like to point out is that if there is no ZOS-specific knowledge in there, you're not going to get to the same level of benefits that we're talking about. You can create false positives because it doesn't understand really what's good or what's bad. It tends to be more focused on symptoms of problems and not root causes, and there's no really intelligence included in that kind of approach to understand where are some resources wasted, or in this particular area of what we're talking about today, how does that impact your peak MSUs or peak MLC costs in the month. So you have a team of very experienced people. If you're like most of the customers we talk to, the problem is you don't have the time to do this kind of analysis. It's really impossible with today's resources levels to apply this kind of expert knowledge across all of the data in a large, complex environment. Even in a small environment, there's many different areas of the infrastructure to look at. And, of course, if you're looking and most days there's nothing interesting to find, I mean, that's just not a good use of time. You need the information really served up to you about what's the most important from a risk and an efficiency standpoint for you to spend time on every day. And so, our goals are to create this kind of platform and intelligence out of the data. And we think it matches well with really what you're trying to do in the performance and capacity area for the mainframe system, is to avoid service disruptions for your production applications, while at the same time, delivering that in an efficient manner. Obviously, it's easy to overbuy on hardware that doesn't guarantee a lack of problems. So we see this as two sides to the same coin, which is why that's here. I mean, the first side on performance problems and performance management, this idea of preventing problems and seeing them before the production environment is impacted is really important, and it's actually extremely rare. The nice thing about RMF and SMF is that it keeps the historical data there. I mean, it really, when you think about it, it is producing the richest source of performance and configuration data in the data center compared to the other platforms, the non-ZOS platforms. It's not even comparable in terms of the richness, robustness of what's involved in the data. So when you go through this process to mine it and apply this expert knowledge and get this early visibility about problems that are developing within the infrastructure or according to best practices, it's extremely valuable to actually avoid these issues. Not everything, as I said, can be resolved. In our experience, when we go back and look at the historical data prior to an issue that's happened for a site in the past, probably about 85% of the time, we can show these are the predictive views you would have been seeing before any real-time monitor was aware that there's an issue or any of the staff. But if that's not the case, where it's a hardware failure or a application change that wasn't tested properly or whatever, it's still very valuable to have all the data there to understand which parts of the infrastructure are impacted, which logical subsystems and so on and so forth, to be able to compare and isolate where the problem is occurring and what the roots of the problem may be. The focus today, though, is really on the other side of the coin, on the delivery of this performance in an efficient manner. So primarily, we're going to talk about optimizing with additional visibility, how many MSUs are required to execute the peak workloads. There is some ways with the architecture to reduce the MSUs with no negative performance ramifications. The other side of the efficiency equation is just in being able to do more with the team that you have, better leveraging the expert knowledge that you have in understanding what's important to look at, what are the remediation actions that you should take. So it's most teams these days are finding it just takes too much time to go out and prepare the data, to write reports, figure out what they mean, to correlate that with knowledge about the physical infrastructure, so on and so forth. I mean, people just don't have the time to do that, and consequently, we're usually behind the curve and more operating in a crisis mode when a problem happens, as opposed to doing some of these things proactively. So a couple of more slides, and then I'll turn it over to Todd. This is an example of this optimized benefit of additional visibility and what can occur. So in this particular chart, it's partially built out. There's 3 sections to it. This is a view that a lot of sites are used to seeing, where they may track their business workloads. In this case, it's the number of transactions per day in the red line. And then the peak hour online MIPS usage is the blue line. So there should be a fairly strong correlation between the two. That's what people are used to seeing. In this particular site, this is a real-world case study, something happened here in where the arrow is, and they began to diverge. And this is exactly the kind of thing that management causes them to say, okay, no new applications on the mainframe, because the costs are just so high. I mean, when the costs of the software, for example, the single biggest line item in the shop, starts exceeding the growth of the actual transactions or business workloads, that's obviously negative attention from management that we want to avoid. In this particular case, what happened at the blue arrow is the site moved to z13 processors. As you probably know by now, I mean, the processor cycle speed is 10% slower than the previous generation, and yet the rated capacity of how many MIPS it can deliver is actually 10% higher. There's some assumptions in there that on how the processor cache is utilized, how efficiently it is utilized. So different levels of complexity of workloads have different characteristics on how they're handled with the new architecture. In this particular case, and it's not an infrequent type of case, the processor cache was not efficiently utilized, driving up the peak MS used during the year for the same kind of workloads. Here's the rest of the story, as Paul Harvey would say, and this is a beautiful picture that's a great way to help the management at the site understand the great work that you're doing in actually reducing costs, even though the red line is continuing to be flat or grow a little bit. In this particular case, after this single area of cache effectiveness was addressed, the MIPS required to deliver those workloads was reduced by actually far more than 20% in this particular case. So as you probably know by now as well, RNI is a metric about cache efficiency. And one of the rules of thumb, as you see what Todd is going to talk about here, is that if you can reduce that by 10%, you'll get about a 5% MIPS reduction. And again, there's no negative performance ramifications on your workloads for doing it. This is like free money as you reduce your software bill per month if you can reduce RNI. In this particular case, because MIPS was reduced more than 20%, basically the RNI was able to be reduced by more than double of what the MIPS was reduced. So hopefully that'll become clear in what Todd presents. At this point, we're going to do a poll. Connie, if you can load that for us. So you see on your screen there in the poll section in the control panel, there's 4 different options, A, B, or C. What's the status of your MLC reduction initiatives? If you could click on one of those options for us, then we will share the results. So the more people that participate, the more interesting that will be. Either you have not yet done significant analysis on MLC reduction, you're at an early stage, you've done some, you're fully engaged in it, or you feel that you're mature, you've already reduced as much as is reasonably possible. So if you can click on those, we will then share the results when we get a good response, and then we'll switch over to Todd, who will go into the concepts on processor cache efficiency and the metrics and how you can reduce that. Okay, the poll has ended. So Connie, you will display the results, I think. Okay, so there they are. 36% have not started yet. 36% are in an early stage. 27% are fully engaged, and 2% say that they're mature, which is pretty normal, I think, particularly because this area of processor cache efficiency is a newer area. The metrics, as you'll see, come from the SMF 113 record, a new subtype that's available if you're on ZOS 2.1 or later. So not everybody has had good visibility into this and how you reduce it. Okay, very good. At this point, we'll switch over to Todd. Connie, if you could pass the ball to Todd. And are you with us, Todd?
All right.
Very good.
Thank you, Brent. Since effective utilization of processor cache is vitally important for the capacity delivered by Z13 processors, let's discuss some of the key concepts behind optimizing processor cache and key metrics that enable us to measure and improve delivered capacity. A good place to start is with cycles per instruction, CPI, which represents the average number of processor cycles spent per completed instruction. Conceptually, processor cycles are spent either productively, executing instructions and data that are present in level 1 cache, or unproductively, waiting to stage data as a result of a level 1 cache or TLB miss. So keeping the processor productively busy executing instructions is highly dependent on effective utilization of processor cache. The second key metric, one that we'll examine in some detail today, as Brent mentioned, is relative nest intensity, RNI, which quantifies how deep into the shared processor cache and memory hierarchy, which is called the nest, the processor needs to go to retrieve the data and instructions when they're not present in level 1 cache. This is very important because access time increases significantly for each subsequent level of cache and thus results in more unproductive waiting by the processor. The formula to calculate RNI as provided by IBM is processor dependent and reflects the relative access times for the various levels of cache. This is the formula for Z13 processors and reflects the percentages of retrievals from various levels of processor cache: level 3, level 4 local, level 4 remote, and finally from memory. IBM defines a threshold value of 1.0, above which a workload is considered to place a high demand on cache and thus may not achieve the rated capacity of the Z13 processors. But no matter what your RNI currently is, reducing it improves processor efficiency, as the upcoming charts will demonstrate. We'll be looking at several charts today from IntelliMagic Vision that provide great visibility into these key system metrics to help identify where opportunities for efficiencies can be found. This chart breaks out cycles per instruction into the productive and unproductive components we just mentioned. The space above the blue line and below the red line on this chart reflects the cycles productively spent executing instructions for a workload. This would be the CPI value if all required data and instructions were always present in level 1 cache, and it's called the estimated instruction complexity, CPI, because it reflects the mix of simple and complex machine instructions in your workload. It may be impacted by migrations to new processor technologies that incorporate internal improvements in processor architecture, but otherwise it's likely to be relatively constant based on workload. So again, think of this as the productive cycles from the earlier CPI slide. But since we have a limited finite amount of level 1 cache, the portion below the blue line reflects the cycle spent waiting for data to be retrieved from processor cache or memory due to level 1 cache misses, and thus it's termed the estimated finite CPI. This IntelliMagic Vision chart breaks out those waiting cycles of estimated finite CPI by the various causes and estimates the relative contributions of each to CPI. The bottom pink band represents additional cycles arising from delays related to dynamic address translation caused by translation look-aside buffer, TLB, misses. The remaining colored bands on the chart represent the components of RNI and reflect the estimated times for accesses from each source. In this example, accesses to level 3 on-chip cache, the dark blue band, and memory on-node and on-drawer, the light blue and green bands near the bottom, are the largest contributors to estimated finite CPI. Reducing RNI means reducing the unproductive cycles spent waiting for data to be fetched from processor cache and memory, improving cycles per instruction and thus processor efficiency. Since this RNI-driven component represents about half of the overall CPI, this is the basis for the rule of thumb that Brent mentioned earlier, that a 10% reduction in RNI can be expected to result in a 5% reduction in MIPS. Reducing RNI indicates improved processor cache effectiveness, which reduces CPU consumption and MLC expense. So how do we go about reducing RNI? To achieve that, first we need to understand hyperdispatch. Hyperdispatch has been around a long time, but it plays an even more vital role on the Z13 processor, where cache performance has such a big impact. There are many aspects of hyperdispatch, but what's pertinent to our discussion today is that hyperdispatch interfaces with the Prism dispatcher and ZOS dispatcher to establish affinities between units of work and logical CPs and between logical and physical CPs. This is important because it increases the likelihood of units of work being redispatched back on the same logical CP and executing on the same or nearby physical CP, thereby optimizing the effectiveness of processor cache at every level by reducing the frequency of processor cache misses and by reducing the distance into the nest required to fetch data. When hyperdispatch is active, Prism assigns logical CPs as vertical highs, mediums, or lows based on LPAR weights and the number of physical CPs. Vertical high logical CPs have a one-to-one relationship with a physical CP. Vertical mediums have at least a 50% share of a physical CP, and vertical lows have a low share of a physical CP and are subject to being parked when not in use. This classification into vertical highs, mediums, and lows is also termed polarity. Having more work executing on vertical highs significantly improves cache effectiveness because that work always accesses the same level 3 cache it was using the last time it was dispatched, and usually the same level 1 and level 2 cache. On the other hand, vertical mediums and vertical lows may be dispatched on various CPs where they will be contending with workloads from other LPARs, making the likelihood of their finding the data they need in cache significantly lower. This set of IntelliMagic Vision charts uses statistics from the SMF-113 records to calculate the estimated life of data in the various levels of processor cache, each graphed over a 24-hour time period. And this provides another data point reinforcing the importance of reducing cross-LPAR contention for cache. In this example, cache working set data remains in level 1 cache for less than 1/10 of a millisecond, level 2 cache approximately 2 milliseconds, and then level 3 cache around 10 milliseconds for most of the day. So by the time an LPAR gets redispatched on a CP after another LPAR executed there for a PRISM time slice of 12.5 milliseconds, its data in level 1, level 2, and level 3 caches will all be gone. The good news is those working sets will be rebuilt from level 4 cache. The bad news is each access to level 4 cache may take 100 or more cycles. This reinforces the importance of having as much work as possible executing on vertical high CPs, thereby eliminating contention for processor cache from other LPARs. So let's look at a case study of the impact of RNI on increasing the amount of work executing on vertical highs. This IntelliMagic Vision chart compares a system's RNI across two separate 24-hour days. On the first day, the system had a vertical CP configuration of 3 vertical highs and 2 vertical mediums. On the second day, the configuration had changed to consist of 5 vertical highs. This resulted in a 20% reduction in RNI, which based on the earlier rule of thumb would reduce MIPS consumption by about 10%. This chart, showing RNI for the same dates and system, but now by logical CP, is very informative because it confirms that the 2 vertical medium CPs, CPs 6 and 8, the light blue and green lines at the top of the before chart on the left, had by far the greatest reductions in RNI. When they were running as vertical mediums, they had a significantly higher RNI than the vertical highs because they were competing for processor cache with other LPARs and their disparate workloads. But when the configuration changed on the after chart on the right, such that these CPs were now running as vertical highs, their RNI was significantly reduced to a level very similar to the other vertical highs. So this clearly confirms that increasing the amount of work executing on vertical highs and thereby reducing cross-LPAR contention for processor cache significantly improves RNI. IntelliMagic Vision provides a number of charts that provide great visibility into the amount of work executing on vertical mediums and vertical lows, which provide the greatest opportunities to achieve RNI reductions and processor cache efficiencies. This chart displays the percentage of general-purpose CP time dispatched on vertical highs for 4 processors over the selected time interval. The processor represented by the red line at the bottom of the chart has the lowest percentage of work executing on vertical highs, and thus represents the largest potential opportunity to gain efficiencies. Drilling down on that processor, this chart displays the MIPS executing on each type or polarity of logical CP over the selected time interval. MIPS executing on vertical highs appear at the bottom in yellow, MIPS on vertical mediums in blue, and MIPS executing on vertical lows in red. And finally, this chart provides visibility by LPAR into the amount of work executing on vertical mediums and vertical lows for the selected time interval, represented by the blue and yellow here. So these IntelliMagic Vision charts provide a variety of viewpoints into the amount of work executing on vertical mediums and vertical lows, enabling a performance analyst to identify the primary opportunities to gain efficiencies by directing more work to execute on vertical highs. So by way of review, delivered capacity on Z13s is more dependent than ever before on effective utilization of processor cache, minimizing the time the processor spends unproductively waiting for data to be fetched from processor cache or memory, as quantified by the RNI metric. A primary way to reduce RNI is by increasing the amount of work executing on vertical high CPs. Since that work executing on CPs dedicated to the LPAR is not subject to contention for processor cache from other LPARs, as is the case for work that executes on vertical mediums and vertical lows. So reducing RNI improves processor cache efficiency, which results in consuming fewer MIPS, which translates directly into reduced MLC software charges. So we've already seen the great visibility IntelliMagic Vision provides to identify the processors and systems where there are sizable workloads not experiencing the improved cache efficiency that results from processing on vertical highs. So what are some actions a performance analyst can take to increase the amount of work executing on vertical highs? Well, as we said earlier when introducing HyperDispatch, the number of vertical high CPs assigned to an LPAR is dependent upon the LPAR weight and the number of physical CPs on the processor. So those are the two factors that we can influence. So first, we can adjust LPAR weights. The number of vertical highs on a high CPU LPAR could be increased by raising the weight of that LPAR, thereby increasing the workload MIPS executing on vertical highs and experiencing the resulting improvement in RNI. The characteristics of workloads on LPARs change between shifts. Automating LPAR weight changes corresponding to those shifts may be another way to increase the MIPS executing on vertical highs. And finally, fewer larger LPARs may be a configuration option to increase the amount of work executing on vertical highs. Second, consider options to increase the number of physical CPs. Installing additional hardware capacity may be a highly cost-effective option in which a one-time hardware acquisition expense may be very rapidly recovered by significant recurring savings in MLC software expense. This was the scenario driving the efficiency example shown in the case study in this webinar. Another way to increase the number of physical CPs without incurring additional hardware expense is to opt for subcapacity processor models. These models provide several additional physical CPs and the associated level 1 and level 2 processor cache for the same MIPS capacity, which translates into more vertical highs. Okay, let me hand it to Brent to do the second poll question.
Okay, great. Thank you, Todd. So you have in your control panel another poll there about RNI in vertical high processor cache optimization. What's the status at your site? And again, we will share these results. If you could click on one of the four options, either not started, you don't know what your RNI metrics are yet, you haven't done that kind of reporting or the vertical highs, or you're at an early stage, option B, you've launched an initiative and are actively exploring the area, or C, you're fully engaged, you know what the RNI numbers are and your vertical high numbers and you're optimizing the situation now, or D, that you have already done as much as optimization as is possible in the area of RNI vertical high processor cache optimization. So we'll give that just a second here to allow people to get over and make their choice. And once the poll is closed, we will share the results. And then we'll get on to the demo of the product that Todd will get into. Okay, so the poll has ended. We can get the results up here in just a second. Okay, there we go. So 70% say they're not started. That, again, is not unusual just because the metrics are newer and not everybody's even on the Z13 yet, where it is more important and more pronounced. 20% at an early stage, 10% fully engaged, and 0% say they're in a mature status where they feel they're completely optimized. So thank you very much for sharing that. Okay, let's continue on then. Todd, are you ready?
Yes. Reducing CPU consumption on Z13 processors through improved processor cache efficiency represents just one area of many that can help achieve significant reductions in MLC software charges. we review a broad range of areas in the no-cost MLC assessments that we offer, leveraging the visibility provided by IntelliMagic Vision into data from your systems. A second focus area is LPAR software configuration. Since the entire MSU consumption of an LPAR is charged for every product that executes there, no matter how small that product's workload may be, LPARs that are configured with a reduced software stack can create an opportunity to achieve savings without any reduction in MSUs. Third, LPAR workload optimization leverages a configuration that includes LPARs with reduced software stacks to ensure that work executes on the lowest cost LPAR that supports the software required by that work, seizing every opportunity to execute work where MSUs are on sale. Since MLC charges are based on the peak 4-hour rolling average for the month, a fourth area is to optimize that 4-hour rolling average, minimizing workload spikes that may drive an abnormally high monthly peak. IntelliMagic Vision provides visibility to quickly drill into the workloads contributing to the monthly peaks, to help identify any work that could be executed at a different time period outside of that peak 4-hour period, and to assist in setting MSU values for LPAR or group caps to manage the work still executing during that peak time period while maintaining the required level of service for time-critical workloads. And finally, batch workload often provides some flexibility in terms of both time and rate of execution. The ability provided by IntelliMagic Vision to quickly identify the size and makeup of the batch workload executing during any interval, drilling down into the components of that batch by system or by service class or by job name, provides the visibility needed to identify opportunities to minimize the contribution of batch to monthly peak 4-hour rolling averages and thus reduce MLC charges. So these potential areas of MLC reduction, along with a couple of others, all played significant roles in the 3+ year MLC expense reduction journey that I led at my previous employer. This chart displays the actual percent expense savings from that initiative in green from the starting point versus the business as usual case in red. When factoring in business transaction growth and IBM MLC price increases and adjusting for one new technology hardware discount, if no actions had been taken, MLC charges would have been expected to increase by 59%. But as a result of these actions, a cumulative actual expense savings of 33% was achieved, demonstrating that opportunities for reducing MLC software charges can be very significant. All right, let's transition into a demo here. Sure that's showing full screen for all of you. All right, so a number of new capabilities and reports have been introduced in IntelliMagic Vision version 8.H, which became generally available this month, to provide visibility into the key processor metrics that help facilitate the types of MLC analysis and RNI tuning that we've been discussing in this webinar. Several of these appear under the processor reporting focal point in the 4-hour rolling average and capping report set. The report currently displayed provides visibility into the 4-hour rolling average by processor. From here, we can drill down into a processor to identify the systems that are the primary contributors to 4-hour rolling average for that processor. And we could continue to operate at the system level, or I'm going to step back here to the KEC level. Now we can drill down here into the RMF interval CPU consumption to see when did increases in the workload consumption at the RMF interval level drive the peak 4-hour rolling average. So we can see it was an increase in this time frame that drove the 4-hour rolling average for the processor to its peak value for this day. And then from here, we can drill down into, say, workloads that are contributing to that CPU consumption. And perhaps this is more batch than we're accustomed to seeing contributing to a peak 4-hour rolling average. So we're going to drill down into that batch by system, and we see that it was primarily running on this system right here. And then from here, we can say, let's drill down into service class, which service classes what they were, and then we could also drill down further into address space names from here. So IntelliMagic Vision gives us great visibility to quickly determine the workload elements that are contributing to the 4-hour rolling average for the selected interval. Now, if we're using WM capping, seeking to manage spikes in the 4-hour rolling average, this chart provides visibility into the duration of when WM capping was in effect for each system. And then if we want to, we can isolate any particular system and see when was WM capping in effect for that particular system. Now let's look at some of the key charts that were also referenced in the presentation that help direct us where to start with efforts to improve processor cache efficiency. This chart provides visibility into the percent of CPU that's executing on vertical highs for each processor. So lower percentages here represent greater opportunities to improve cache efficiency. So let's drill into MIPS by polarity for this processor here at the bottom. And again, this is the view that shows the amount of MIPS that were executed on vertical highs, on vertical mediums, and on vertical lows. This report provides an LPAR view into MIPS by polarity. And again, so the MIPS in blue and yellow here represent MIPS that are executed on vertical mediums and vertical lows, which can be our primary opportunities for processor to implement processor cache efficiency. And perhaps we want to zero in a little bit on a certain set of LPARs here, and so we can customize the chart and then just look at the LPARs that we have that are of particular interest. Now let's look at the visibility IntelliMagic Vision provides into the relative nest intensity for that same set of systems. As we discussed, RNI is a primary metric to measure the delay a workload experiences waiting on data and instructions to be fetched from the cache and memory hierarchy so that they can be executed. So improving RNI is a significant area of focus for improving processor cache effectiveness. So let's zoom in on one particular system here and see the RNI for this system. Now, in this environment, a hardware change was implemented to increase the number of vertical highs available to this system. So we changed the date interval to the date after that change was implemented. And so now here's the resulting RNI. If you're like me, it's a little difficult to remember exactly what it was on the previous chart. So IntelliMagic Vision provides the capability to very easily compare two time intervals in the same display. So here we see that the RNI was reduced by over 20% from that change in the vertical CP configuration. Now, we spoke in the presentation of how much more efficient work is when it executes on vertical highs because it avoids contention for processor cache from other LPARs. So let's drill into this data now by logical CP. And I'm just going to remove the zips here because those are not what we're focused on in this analysis. So here we see at the time of the before chart on the left, we see the two logical CPs, CPs 6 and 8, the light blue and green lines at the top of the before chart on the left, how much higher their RNIs were for those two logical CPs than for the other three logicals that were vertical highs. And at the time of the after chart on the right, The vertical CP configuration had changed so that all 5 CPs were vertical highs. And note the magnitude of the reduction in RNI for those 2 logical CPs 6 and 8. And so this was the primary factor that was driving the 20% plus reduction in overall RNI for this system that we saw earlier. All right, this concludes my demo, and so now I'm going to hand it back over to Brent.
Great. Thank you very much, Todd. Very interesting stuff. Let me just talk a couple of minutes. We're getting close to the end of the hour here, but I want to talk about an MLC Assessment Offer. So I believe Todd is one of the experts in the country on the different ways. He talked about 5 different areas that we look at, including some capping kind of topics in the batch optimization area, as well as RNI and software reconfiguration, LPAR reconfiguration. So what we're making available is basically some of Todd's time for no charge to look at your data and help identify some opportunities at your site that are yet unrealized. So the way that works is basically you FTP some RMF and SMF data to us. It's a pretty simple process. It'll take somebody about half of a day to access our RMF pack collection process, select the record types, and send it off to us. And then we will do an analysis and present the results in usually about a 2-hour meeting with the entire performance and capacity planning team, and there's a lot of good interaction back and forth. So we've been doing this for about the last 6 months. There's no charge for that if you're in North America. And we're using our software as a service platform. That's what Todd did the demo on. This is a little diagram that shows how that works. And basically, you will send the data, and we'll process it and create the metrics and intelligence. And then afterwards, you can actually get access via the web reporter. It's very quick and easy to install, or there's a Windows reporter that has a few more capabilities in it as well to access the same thing that we use to produce the presentation about the identification of MLC reduction opportunities for your site. So we've been doing this, and it's been a very great experience to see the data at many sites and help a lot of different organizations to see the opportunity to reduce their software costs and to help them do that. So that's really the end of the prepared material we have. We only have a couple of minutes left. Janine, are there some questions that we should address?
There are, Brent. Okay, we'll get started. Does SMT have an impact? If so, how?
Okay, Todd, I'll let you take that.
Yes. So this is Todd. So currently SMT is only activated for ZIP processors, not general purpose CP processors. And MLC is based on general purpose CP. Any workload that you can run on ZIP CPs is exempt from MLC, so it's absolutely to your advantage to do as much work that you can on ZIPs. So SMT just enables you to extend the capacity, your hardware capacity of your ZIP processing there, but it does not relate to MLC reduction.
Okay. Next question. I just minimized my screen. I'll move on to this one. If our RNI is already below the 1.0 threshold IBM defines for high workloads, is there still any benefit to seeking to reduce that further?
Yes, there is, because the same rule of thumb applies. A 10% reduction in RNI will translate into approximately a 5% reduction in MIPS consumption. So yes, there's definitely still value. It's just the potentially the amount that you can reduce your RNI may be a bit less if you have a lower starting point than if you start from a higher value.
Okay. You said one way to increase the amount of work resulting or executing on vertical highs is to add surplus hardware capacity, which costs money. Doesn't that offset the savings from MLC reduction?
So we believe that the economics of a one-time acquisition of hardware capacity may very well significantly that may be significantly less expensive than the recurring, ongoing, year-after-year savings that you will achieve through your MLC reduction. So each site would have to do that particular financial analysis themselves, but we believe the financial case there can be very compelling.
Okay. I think we have time for a couple more. Are these concepts also applicable to other platforms like the EC12?
So the general concepts that we talked about today about, your cycles are either productive or not unproductive, and that reducing RNI, which reflects improved processor cache efficiency, will reduce CPU. All of those concepts are applicable to all other IBM processor platforms as well. The amount of impact is just greater with the Z13 because the Z13 is more dependent upon processor cache efficiency because of the cycle speed considerations that Brent talked about at the beginning.
Okay. Is there a charge to get your recommendation after sending SMF and RMF to you? I think that's referring to the offer that Brent talked about.
Yeah, there's no charge. There's no obligation. We come and present our findings to you in that sit-down session that Brent talked about, and then we just decide together whether to go forward from there.
Great. What would be the maximum outage or impact we can expect during the change? I think if they were to adopt this.
Yeah, I'm not sure I probably quite understand the nature of the change that's being referred to in that question.
Okay.
I mean, the product in terms of modernizing the approach to RMF and SMF data doesn't require any outage and doesn't impact availability on a system. It just involves providing the data and having it processed as software as a service that Brent discussed. So there will be no impact to availability on a system for a site to get the benefit of having the visibility that IntelliMagic Vision provides for your RMF and SMF data.
Okay, great. Unfortunately, we have reached the top of the hour, and I know we didn't get to everyone's questions. So just know that if we have not addressed your question, someone will follow up via email to answer it. I want to thank everyone for attending today's webinar, and I especially want to thank Brent and Todd for sharing their expertise with us today. We also had a number of requests for the slides, so I just wanted to let you know if you're interested in receiving the slide deck, go ahead and send me or Brent, send it to me or sales@IntelliMagic, your request, and I'll make sure that Brent gets it. As IBM Systems Magazine will only be sending out a link to a recording of today's webinar to everyone on the call today, as well as to anyone who registered but for whatever reason could not attend. And feel free to put your request also in the Q&A panel. If you'd like to receive the deck, you could do that now, and we'll capture that then and be sure that we get that to the folks at IntelliMagic. Very good webinar today. Thank you for your questions and your attendance. That concludes our webinar. Thanks again, and have a great day. And then, Connie, let's leave the event open for a moment. I'm getting a lot of requests for the slide deck. Thanks, everyone.